Hello everyone and welcome. My name is Ulises Velasco Garcia, and today I'm talking about numerical methods for the direct nonlinear Fourier transform on the nonlinear Schrödinger equation. This is a joint work with Dr. Vladislav Kravchenko and Sergey Torba from Simvestab Querétaro. And before I start, I would like to acknowledge Dr. Gerardo Hernandez Dueñas and all the organizer of SIAM annual meeting 2021. So first in this conference, I would like to introduce to you the nonlinear Schrödinger equation, of course, and what's the Sakharov-Shabbat system as a Sturm-Liouville equation. And the main idea I would like to present in this conference is uh, methods to solve Sturm-Liouville equations. Sometimes Sturm-Liouville equation might be difficult to solve, but with those methods are a lot easier to solve, especially when they have non-constant coefficients. And for the end of this conference, I would like to present to you some numerical examples to show that this actually works. So the normalized dimensionless non-stochastic Schrödinger equation is really similar to a heat equation where we have this non-homogeneous nonlinear term. I is of course the imaginary unit, and Q is in general a complex value function where X corresponds to a real a variable, and T represents the time, and then is also a real variable. So what's a nonlinear Fourier transform? It has three main important steps. We're going to focus on the first step for this conference, and I'm going to talk about a little bit in this slide about the other two steps, which I am not working on this conference. So to solve the nonlinear Schrödinger equation, we first restrict t to a particular time, for instance 0. Then we get some data called scattering data for a particular time. We generalize that scattering data for a general time. This is not complicated, and via an inverse problem we can construct the solution of the nonlinear Schrödinger equation. This step might be an ill-posed problem, so we need high precision on the scattering data. Okay. So when we're studying the nonlinear Schrödinger equation, it reduces under the nonlinear Fourier transform to a differential system, which is called the Sakharov-Shabbat system, and is actually this system I'm presenting here, where lambda is the spectral parameter, Q is the same complex function I was showing for the nonlinear Schrödinger equation with a specific time, for instance 0. Star represents the complex conjugate. Remember that this is in general a complex value function. And we're looking for this vector v, which is actually two functions, v1 and v2. And for the boundary conditions, we're going to consider the just function, which are defined by asymptotic behavior at infinity and minus infinity. Basically, we want it to behave like exponential functions where the argument is related to the spectral parameter. Okay. Well, we also have definition for the spectral coefficients. Those are defined by the limits of two of the just functions I just presented on the last slide. We're just taking a limit where x tends to infinity. All right. Okay, so I'd like to show to you this definition for the scattering data. We have the continuous and the discrete spectral functions. So the discrete spectral functions, yes, are the division of the spectral coefficients, where we have a derivative by lambda for the A spectral coefficient, and this is called Q tilde, and Q hat is also a division of the spectral coefficients. Look that this function is discrete. Okay, it's just defined on the spectral values. I mean the eigenvalues. Yes, and this one is continuum. Okay, this is the continuum spectrum. All right, so if we consider a compactly supported potential, which is a really usual ansatz, we simplify everything a lot. For instance, the boundary conditions, I mean the just solutions for the Saharev-Shabat system, reduced to these boundary conditions on the segment, on the compact segment, and also the spectral coefficients are going to be simplified a lot. Okay, where A and B are just defined on the boundary of our compact set. Yes. Okay. So, what's the relation of the Saharev-Shabat system with a Sturm-Liouville equation? Okay, we have two situations here. When we consider a complex value function, which is the case I just showed a few slides ago, we obtain a very special kind of Sturm-Liouville equations, which are called bundle Sturm-Liouville equations, or also pencil Sturm-Liouville equation, where the difference to a usual Sturm-Liouville equation is just that the spectral parameter appears two times. This is power 1 and power 2. Okay, this is a bundle Sturm-Liouville equation. So when we consider real valued potential, which is a particular case of this Saharev-Shabat system, we obtain a classical Sturm-Liouville equation. It's very important to consider that it is only possible if the potential Q is compactly supported and non-vanishing on this interval, this closed interval. Okay. So how can we solve this bundle Sturm-Liouville equation? This is the method I would like to present to you. This is called the spectral parameter power series, SPPS for the abbreviation. So we're going to suppose that on a finite segment, compact finite segment, closed, this particular equation possesses a particular non-vanishing solution. We can guarantee that by the Weil theorem. Okay, this is really easy to build, such that the function v0 divided by q star belongs to the C1 space, and the functions that we have here are continuous on this finite segment. Then a general solution for the bundle Sturm-Liouville equation has the form of C1 G1, C1 times G1 plus C2 G2. Those are the linearly independent functions. Of course, C1 and C2 are arbitrary complex constants, and G1 and G2 are spectral parameter power series. Look, that lambda is the spectral parameter, okay, and we have these special functions x tilde and x capital X, okay, where it's really easy to build those functions. Okay, so these functions are also called formal powers, x tilde and x, and are defined as follows. Are just recursive relation. They are going to be 0 for every n, negative n. Okay, for when n is equal to 0, they are going to be 1, and when n is positive, okay, they are defined as follows. They are just an integral from x0 to x, and we have the coefficients we talked about before. That's why we needed them to be continuous. Okay, we needed them to be continuous for this integral to exist. Okay, x0 is an arbitrary point in the closed interval, and both series in G1 and G2 converge uniformly on the segment A from A to B. Okay, this is really good because when we are approximating the numerically the series, we are going to need a few of them. So this is an original theorem we are presenting. Okay, this is a representation of the nonlinear Fourier transform of the nonlinear Schrödinger equation with a complex valued potential Q, compactly supported and non-vanishing on this finite segment from minus A to A. Okay, this is actually a spectral parameter power series representation. All right, where we take x0 as not as an arbitrary point, but the beginning of this finite segment. Okay. So this was published in 2015. Okay, and this is also a result I would like to present to you. This is a term: the continuous and discrete nonlinear Fourier transform from the nonlinear Schrödinger equation with a complex value potential Q, compactly supported, of course, on the non-vanishing segment minus A to A, are as follow. Okay, where we are taking x0 equals to minus A for the auxiliary functions. The importance of this representation, because they might not look very beautiful, is that the representations we found on the other papers were built for an specific potential where we have few restrictions for the potential in this case. So the second method I would like to show to you is called analytic approximation of transmutation operators. Okay, so if we consider an Zagreb-Shabat system with a real valued potential, we get these supersymmetric partners, which are Sturm-Liouville equations, and we have a particular solution for lambda equals 0 of these equations, which is e power minus the integral of x. All right. Okay. Whose p? P is equal I times q. All right. We have a very slight change of notation. So once we have a classical Sturm-Liouville equation, we can apply a transmutation operator, which is actually an operator. Okay, this is the definition of a transmutation operator. Okay, where T is an invariable operator defined on a topological space. It's invariable, and it satisfies two conditions. Two conditions. T and the inverse are continuous on this topological space, and this equality is valid where A and B are also linear operators, where E1 is a linear subspace, not necessarily closed. So we're interested on a particular case of that theorem. Okay, A and B are differential operators. Okay, G is a continuous complex value function for the first operator A. E1 is the C2 space from minus A to A. Okay, and it is possible under those conditions to construct a transmutation operator T, which maps a solution V of the equation BV of x equal to omega square V of x. For instance, the double derivative of x of v plus omega square v of x equals to 0, where v is actually another name for the spectral parameter. Okay, into a solution of this more complex equation. Okay, which is also this is actually a Sturm-Liouville equation, where this is the spectral parameter. Okay, and I'm sorry, I'm just missing u of x. I'm missing a u of x here. Okay, otherwise it wouldn't work. I need an u of x here, multiplying g of x, in order to get a Sturm-Liouville equation. Okay, I'm sorry for the mistake. With the following correspondence of the initial values, which are u of 0 equals to 0, 0, and this initial value, where h is in general a complex constant, not very important. Okay, so the transmutated solution brings a solution of this simple equation to a Sturm-Liouville equation, where we have the u I was talking about. So if we consider two particular solutions, for instance, the cosinus of omega x and sinus of omega x divided by omega, we can obtain a Volterra integral representation of the transmutation operator. Okay, so the solutions of this Sturm-Liouville equation satisfying these initial conditions are going to be represented by those solutions, okay, C and S, okay, where we know how to approximate the kernel of this integral representation. The kernel, okay, it is really easy to build. We just need those S of n and C of n representation, which are series, and phi is related to the formal powers x tilde and x I was talking about before. So this might look like a different version of the SPPS method, but this is not a different version of the SPPS method, because the properties are very, very, very interesting. Okay, and then I'm going to show in a few slides the properties of each method, the SPPS and AATO. So let us consider the simplest potential. Okay, this is just a square. This is really simple. Let me see if I have, well, I don't have a schematic, but it's just square. I mean this is 0 on all the reals, and in the closed interval from t1 to t2 is just a constant a. Okay, this is known as the rectangular profile. So if we run the examples, okay, we have the exact continuous and discrete spectrum for this potential, okay, and we have the results here. On green, we have the exact solution, and look, the AATO is very precise when we are away from the origin, okay, because remember we divided by the spectral parameter, so numerically it behaves so bad near 0, but we have that the SPPS method works really well near 0, and then it stops working. Okay, we can also see that here the AATO method, the spectral parameter, I'm sorry, the analytic approximation of transmutation operators works really bad near 0, but the SPPS method works really well, and the SPPS method stops working. Okay, this is a comparison of the continuous spectrum of the two methods. Okay, we also are comparing the absolute error of the SPPS method and the AATO method for the continuous spectrum. Look, the SPPS method works really well near zero, and the AATO methods it actually doesn't work near zero, but works really well when we are away from zero. This is a very interesting behavior. So we can mix, yes, we can mix both methods. For instance, for the discrete spectrum, we have this numerical experiment um, for various values of a. For instance, a equals 2, a equals t, 3, and a equals 10, where we have this level of error on the discrete nonlinear Fourier transform. Okay, and I think my time is finished, so thank you very much for your attention.